Okay, so number 4 of this series is once again a net force problem. Now we have a wagon, which I've helpfully drawn in here, which is being pulled along by a rope in a horizontal or on a horizontal force, on a horizontal surface. Let's try that again. The force in the rope is 4 newtons, and the rope is at an angle of 70 degrees to the horizontal. We give some information that the force of gravity on this wagon is 16 newtons, and the ground is pushing up with an unknown force. That's that normal force that we talked about before. I've drawn the normal force as being evenly split between the two wheels, but when we actually go through this problem, we're not going to talk about it as being split. We're going to talk about it as being a single normal force, because we don't have any particular portion of the problem where splitting it between the two wheels, I guess 4 wheels strictly speaking, the 2 axles, makes any sort of difference. Notice 2 things about my notation. F sub n is the normal force by sort of agreement and standard. F sub lowercase g is the force of gravity. So let's talk about what's going on in this situation. We have a 4 Newton force that's operating at an angle. Like we've seen right along, we're going to break that force into a vertical component and a horizontal component using that same SOHCAHTOA method in trigonometry like we've seen. So the vertical force component here is the hypotenuse times the sine of 70 gives you the opposite side. So 4 sine 70 gives you the magnitude of the vertical component of the force at 3.8 newtons. And this is the adjacent side. Adjacent over hypotenuse equals cosine of 70, or 4 times the cosine of 70 gives you the length of that side. The magnitude of the horizontal component of the force is 1.4 newtons. Now, in order to answer any further questions about this wagon situation, we have to do a little bit of addition. Vector addition specifically. So let's take a look at this problem again. We have only one force acting in the horizontal direction. We agree that the wagon's going to move in this direction. The wagon is, that's a really bad line because I'm writing on a bad surface. So the wagon is going to move in the horizontal direction. The wagon is moving in a horizontal direction due to a net horizontal force of 1.4 newtons. The wagon is not moving in a vertical direction. That's the standard way wagons move, right? They don't float off the ground. They don't sink through the ground. They move along on the horizontal surface. We have a 16 Newton force pulling down on it. We have a normal force by the Earth's surface, which is of unknown magnitude, and then we have another vertical force on this wagon which is counteracting the force of gravity on the wagon in part, and that is the vertical component here of the force in the rope. We found that that was, remember, 3.8 newtons. So now the upshot of this is that we have a normal force on the wagon, which is unknown in magnitude. We have a sort of pulling force on the wagon. This is now just looking at what's happening vertically, of 3.8 newtons. We have our wagon here. And then we have a force of gravity down on the wagon of 16 newtons. Of course, we also have that horizontal force on the wagon, but we're going to ignore that for now and just think about the vertical situation. Because the wagon is not floating off, nor is it sinking through the ground, we know that the vector sum of the upward and the downward forces have to be equal. So 16 equals 3.8 plus the normal force. And here we are here. So the net vertical force has to be 12.2 newtons. And that 12.2 newtons is the normal force. Sorry, that's not a net vertical force. The vertical force has to be 12.2 newtons here, which is the normal force, plus 3.8 newtons, both of these up directed, to balance out the force of gravity downward on the wagon. The final question that that we're going to consider, the final two questions, I guess, that we're going to consider with respect to the wagon. Now that we know all the forces on the wagon, question 5 asks, well, okay, if the wagon mass is 1.6 kilograms, what is the acceleration of the wagon? So we know that we have a net horizontal force that we calculated before of 1.4 newtons. That's in the rightward direction. Mass is 1.6 kilograms. Rearrange our traditional way of thinking F equals ma to be A equals F over m. Acceleration is force divided by mass, Newton's second law. Plug in our numbers. Interesting. 1.4 newtons divided by 1.6 kilograms. Suddenly we don't know what to do with our units. Remember how in the first or second lecture I put up a particular slide that showed how many of our standard SI units are derived from others. So this is something I'm doing explicitly here. Newtons is actually kilogram meter per second squared. Now we see that our units kilograms cancel out. We are left with the units meters per second squared. We're looking for an acceleration, so this is reassuring. And we find that the wagon accelerates at 0.88 meters per second squared in the rightward direction. All right, and the final question, number 6, that we ask regarding this wagon is if the wagon starts from rest, v0 equals 0, and it's accelerating as we calculated from the above, then how fast will it be going after 10 seconds? So just as we did with those first couple of problems with the car, current velocity equals original velocity, here 0, plus the change in velocity, which is due to the acceleration, which is given by acceleration times the time. 0 plus the acceleration times the time gives you 8.8 meters per second. All right, great. One more question we can ask about this foolish wagon, which is, all right, at that point at 10 seconds, how far will it have gone? Current position equals original position. We never gave the original position of the wagon, did we? This is one of those places where you, as the person who is calculating out the problem, are powerful. You can decide that the wagon has started at position 0 meters. We said that the wagon started at rest, v0 equals 0, so these two terms drop out as zeros, and then we have that 1/2 at squared portion of the formula, where again remember that 1/2 is coming about because there's the area under the velocity times time curve